Let us begin with our next topic. Last time we were done with the first part of the expectation, and that was the mean of a random variable and the mean of a transformed random variable, and so on. We had a few examples as well. So this variance is important because if you remember, we discussed the mean, expected value of a random variable. This was coined as a typical value, typical value. So what it meant was that if you have, let's say these are different trials, 1, 2, 3 and so on, the experimental trials, and these are observations, and you get these different observations, and so on. So mean is a single value which can replace all of them, so which is representative of all of them, in the sense that if you take the distances of all these observations from this single observation, the sum of squared, so actually we introduced the mean as a typical value in the sense of minimizing the sum of squared Euclidean distances from long run observations. So let's say you have a long sequence of observations. So we found there that this sum of squared distances of all the values, all possible values of some random variable, and remember this was the absolute frequency, absolute frequency, because in this long sequence of trials, values will be observed more than once, so we have to record the frequency of observation of value k. So if this mu n hat is to be the typical value in n trials, representative of all values of the random variable, this sum must be minimized by the value of this number, and we proved in the previous lecture that if you try to minimize it using calculus, this typical value must be of this form. Remember, this was the absolute frequency, and if you divide this absolute frequency by the number of trials, you get the relative frequency. This was the typical value for n trials. And you should also remember that we then use this to define our abstract mean as a long run average. So then you typically allow n to get larger and larger without limit, and then our definition of the mean was that we sum over k all values, and this relative frequency was replaced by probability. This was just to refresh your memories of that lecture. This is how we introduce the mean as a typical value or as a representative values of observations in a long run sequence of Bernoulli, actually in the Bernoulli trials. So Actually, you don't need Bernoulli trial, you just need independent trials. Yeah. So now we can ask another question. Okay, we are done with this typical value. So now we want to know the spread. What will be a measure of spread of a distribution? You know, these values are not always close to the mean. They are actually spreading around. So a measure of spread, I mean, it is, of course, it is in the literature, it's called the standard deviation, and we use the symbol sigma for that. That will be seen as the Euclidean distance between a typical pair of values. Yeah. It will be between a typical pair of values. So just like this mu was a typical value, now we are searching for a typical pair of values, and the distance between those two values will be a measure of spread. So instead of looking at all the possible pairs, we look for a typical pair. Now, what will be that typical pair? Yeah. So I am looking for a pair of values which can be used as representative of all the possible pairs, and the distance between those 2 points will be my standard deviation. That standard deviation will be used as a measure of spread. Now, if you are careful, I already know one of the components of this pair, and that is the mean. Okay? Because if mean is a typical value, it must be part of this pair. If you say, oh, I should look for another value, then why you picked this as your typical pair? So that is clear that one of the components is a pair. Now, what is this second component? Now it's very clear. You have 2 points. One is mu. The other is such that the distance is sigma. We don't know the value of sigma yet. It's just something we are looking for. So if you are careful, this can either be mu plus sigma, because we are on the real line. Yeah, on the real line I have a typical value mu, and I am looking for another point which is at a distance sigma. So one possibility is mu plus sigma. What is the other possibility? That I go in the other direction, keeping the same distance sigma, and that will be mu minus sigma. So this pair can only be in this form. Yeah, it will be mu either plus or minus sigma. This is the key to actually find an expression for this sigma. So let's move on. And remember, we use the subscript. We use the subscript n because this is the abstract theoretical mean, and this subscript n and the head is actually its estimate using data of in trials. So which means that when we use the same data obtained in n trials, this will be approximated or estimated by something represented by a head, because we do not have access to that theoretical quantity, and I use the subscript n to remind me that this estimation is based on the data of n trials, yeah? Just like we did for the mean. So yeah, I actually explained all that here in the paragraph for you to read. So now I have identified the form of that typical pair. And what is the distance? What is the distance between the two points of that pair? That is sigma n. Yeah? So actually, if you look for a sign, distance will be plus minus. So that could replace, if we go back to that formula, basically I have written the formula there, that summation, yeah, which was minimized by this number. If I replace all these squared distances by the typical distance, yeah, which I don't know the value, but I know the form of the pair, so that this will be my typical distance, and these are the actual distances. So if I claim that this is a typical distance or a representative distance, so it should be possible for me to replace all of these observations with this single uh, distance, and the sum must not change, because if the sum is changed, then it's not a typical value. So this can, because this doesn't depend on k, it can be taken out, yeah, and sum of all the frequencies, yeah, sum of all the frequencies must be equal to the number of trials, because you have n trials, so all the frequencies must add up to n. So that n appears here, and because sum applied to that is n, and this plus minus squared is actually always plus, so you get that. Now what does this tell us? That we can now use this equation to discover an expression for this estimate of our spread. Just take this n to the other side of the equation and you have your formula. It happens to be the average squared, because this is the average, this is the sum of squared distances. If you divide that sum by n, you get the average squared distance per trial. So my intuition for a measure of spread is this. It is basically the average squared distance per trial. So I just plug this value, and I remember that absolute frequency divided by the number of trial gives me the relative frequency. So I can use this as a guideline for my actual definition. Remember, this is not a definition. This is just an expression we obtain for n trials, yeah, for our estimate of spread in n trials. So I can now replace these relative frequencies. I can replace these with probabilities, and that will give me a definition. This can now be a definition of the squared actually spread. So the measure of spread is actually sigma itself, because that is a distance, and this formula gives me the square. So the name for this measure of spread is standard deviation, as mentioned earlier, standard deviation. And the formula I discovered is not for the standard deviation, but for the square of it. And this goes by the name variance. So variance is by definition the square of standard deviation. So standard deviation must be the positive square root of the variance. So once I'm done with this, I can simply take the positive square root of this, and I'll get my measure of spread. So if I want to limit myself to a particular random variable, a general random variable, we'll denote this by variance x. Variance is an operator. This is another notation, just that sigma squared with the subscript x. And you can see that this can be seen as the expectation or expected value of this transformation. You see, if I use this transformation, x will be replaced with k, mu will be replaced with mu, and that is actually one thing should be clear here, because this is a definition. I should remove the hat. Yeah, this hat should not be there. This hat was only when we were using the data of n trials. Now we want to replace the relative frequencies by theoretical probabilities, and their n must disappear. So this will no longer be an estimate. So here is the summary. The summary is for those guys who could not follow this reasoning. At least you know how to work out the expectation of any transformation. You already know that. Yeah? You know how you work this out. So if I replace this transformation with x minus mu x, the mean of x, and I square it, this is my transformation g of x, and if I work this out, this will give me the variance. You can remember it this way. Yeah? An alternative representation is sigma x squared. So it's up to you whether you just go for this formula, remember it. You will remember it because you will be using it a lot, or go with my explanation. I actually told you the meaning of variance. Yeah. And this slide will shed more light on the meaning of variance, spread, variability. If you see these four pictures, it shows the dot throwing actually activity, and here you can say that okay, there is a small variability here. Yeah, so the standard deviation here will be very small, and you are hitting the target, so the mean value is also um, at the right spot. So here, and you can see it there. Yeah, the distribution or values are distributed around the mean, and the spread is not very much. But here, although you are still around that same typical value mean, but there is too much spread. Yeah, the values are scattered away from the mean, and these two are actually other examples where, although the spread or variability is small, the mean is actually away from the required value. And here actually it's worst in all senses. Not only the values are scattered, they are also away from the desired value. So if you can recall measurements from your school time, there you must have uh, heard two names. Actually, there were two terms. One was called precision, yeah, and one was called accuracy. So now you can remember that what we mean by variance or variability is actually a more technical term for precision. So high precision would correspond to low variance, and high accuracy would correspond to actually being very near the actual or true mean. Yeah. So if you are away from a desired mean, you will have low accuracy and so on. So now that we have discovered a new quantity, variance, we can ask whether this is linear or not. So I just use a linear transformation. So let's say g of x comma y is a linear transformation, a times x plus b times y. So if variance is linear, I should see this. that the variance of this linear transformation should give me A times the variance of x plus B times the variance of y. If variance is linear, I should get this. But you will see now that it is not the case. In general, variance is not linear, and then that you can establish simply by using the definition of variance. Variance of z by definition is the expectation of this transformation, yeah, squared deviation and the expected value. Now just plug in this value here, yeah. So I replaced z with this transformation, and I also know that the mean of this z, I already know how to work that out. That is E expectation of ax by, and because expectation is already linear, it will simply be a times ex, which is the mean of x, plus b times ey, which is the mean of y. So I plug that as well here. So it is just an expanded version of that. Then I apply the square, yeah, sorry, it is 2ab, I got it wrong again. So I hope I remember it to fix it in the actual document. And I apply expectation as a linear operator, and at the end I get this actually formula. Now it is very clear that because of these coefficients, they are not, if it were linear, you would have simply a times this and b times this, and you have squared. So that is one way in which it is non-linear. But most important, you have a term at the end, even if a and b are 1. Let's say if I set a and b both to 1, okay, this will disappear. So I can say, okay, at least for a is equal to b is equal to 1, this should be linear, but even then it is not linear, because this term will always bother you. So we can look for conditions under which this term is also 0, but before that, let's define, because we actually have discovered a new quantity. So I can, just like I took this as my transformation, I can see this x minus mu x and y minus mu y, sorry, as a new transformation. I can just call it h. Let's name it h, not g. Let's say it is h of x comma y, yeah. And if I now take the expectation of this, I have discovered a new quantity. So this quantity is called covariance between two random variables. This is how we will write the covariance, because it tells you how x and y vary together from their respective means. Yeah? X deviates from its own mean, y deviates from its own mean. We multiply the two and then take the expectation, so that's why it's called covariance. Yeah? And this will be the theoretical integral. I mean, you don't need to do this, it's just a reminder. So when will this be 0? One way in which it can be 0 is to recall that we observed something, that this joint CDF, under one condition, this can be factored into the one-dimensional PDFs, which we also call the marginal, so this joint CDF can be factored into these one-dimensional CDFs, and these were also called marginal CDFs, if you remember. Yeah. In simple words, if x and y are independent, then all the probabilities associated with x and y, all the events associated with x and y will be independent. And you know what happens in independence is that two events being independent, the probability of their intersection is simply the product of probabilities. And you should remember that this joint CDF is also a probability. This marginal or one-dimensional CDF is also a probability. This is also a probability. So these probabilities multiply actually in this sense, and that's why we say that x and y are independent. That is one way in which this will be 0. Now why will this be 0? If I factor this, if I isolate fx and fy, yeah, so this double differential will split into these two differentials, dfx times dfy. This dfx will be combined with this deviation, this dfy will be combined with that deviation, and this double integral will simply be two integrals. Yeah, one integral of that deviation of x integrated with respect to its CDF, and another integral of deviations of y from its mean integrated with respect to that particular CDF. So if you look at this, I have factored that double integral into two integrals. But remember, these are not squared deviations, these are simply deviations, and it will, if you work this out, it is simply the expectation of x minus mu, and that is simply the expectation of y minus mu y, and you know both of them are 0, so the answer is 0. Yeah, so the covariance between two random variables will be 0 whenever x and y are independent. That is one way of getting a 0 here. But you will see later on, although at this point I don't want to go into that detail, it is possible for x and y to be dependent and still this will be a 0. That will be because of some mathematical properties. We don't go into to that discussion, but I just share with you a name of that. So x and y in general are said to be orthogonal if the covariance is 0. So whenever you find out that the covariance between x and y given by this formula is 0, you will say that they are orthogonal. One special case of orthogonality is independence, which we discussed. Remember, independence is one way in which covariance is 0. Because there are other ways, so we have a more general name called the orthogonal random variables. So if I go back to this definition, now I can say that at least for orthogonal xy or for independent xy, this will be 0. Yeah? And I'll only be left with this. So I will pick this point and I can now state a more useful result. So this will be useful for this course from now onwards. If we have a sum of two independent random variables, the variance will behave like that. If I apply variance operator to a linear combination of x and y, a and b are constants, the variance will have this form. It's still non-linear because of the square coefficients, but at least I can remember there is some organization for remembering it. So variance of a times x plus b times y is simply a squared times variance of x plus b squared times variance of y. And if I generalize this to a linear combination of n random variables, coefficients are a1 up to an, the same rule applies. It will be a linear combination of variances, but each coefficient replaced by its square. So this is actually something which I would encourage you to remember, provided that the random variables are independent. Now if we choose all these coefficients to be 1, then we have an even simpler version of it, and that is simply that variance of sum of random variables is sum of variances provided they are independent. So we can now use these ideas to have a few random variables. Actually it's not 2, there are many, I added some. So if you start with direct distribution, meaning that You have a deterministic quantity A. So deterministic quantity does not vary at all. It's just a single value. So actually this spread is 0. So the variance is 0. And if you apply the formula, you will still get a 0. So there is no rocket science there. If I move on with Bernoulli distribution, I know the Bernoulli distribution has a mean equal to P, which is the probability of success. It is also the mean. I can now use the formula of variance to work out the variance of a Bernoulli random variable. So variance of x will be sum over all possible values, which is 0 and 1, squared deviations, k is any value, minus the mean. You subtract the mean, then you take the square, and then you simply multiply it by the probabilities. And these are the probabilities, remember, discrete PDF. Work it out. 1 minus p, 1 is the success, so the probability is p. Here it will be actually 0 minus p, and 0 minus p whole squared is p squared, and you multiply this with the failure probability, and that is your result. So it turned out that we have a very simple relationship for the variance of Bernoulli random variable. If you want to remember it, don't remember this formula, remember it this way. It is the probability of success times the probability of failure, because that statement frees you from any notation. This is p. In another book it could be theta, in another book it could be actually mu. You don't care. It is always probability of success times probability of failure. That will give me the variance of a Bernoulli distribution. So I can here ask a very interesting question, which I forgot to ask when I was actually lecturing. Because p can have any value, I can ask myself for what value of p will I get maximum variance. So I am talking about the Bernoulli family of distributions. For each value of p, I will have a Bernoulli random variable, and I am wondering which of those Bernoulli random variables, which member of that family will have the highest variance. So that is very easy. I just want to maximize this. So I differentiate this, set it to 0. So just expand this, it will be p minus p squared. Differentiate this with respect to p and set it to 0. So derivative of p is 1, derivative of p squared is 2p. Set it to 0, and the value of p which maximizes variance is half. Yeah, this is actually, I already told you something. The maximum uncertainty, yeah, is when you have no clue and you simply say, okay, p is equal to half, means that you have maximum uncertainty. That maximum uncertainty coincides with maximum variance. Yeah, this is another way of looking at it. If you want to use this result for a 2-point distribution, so instead of 0 and 1, you have a and b. Without changing the probability, you still have p here, sorry, 1 minus p here and p there. Here the probability of a will be 1 minus p, and the probability of b will be p. So you just recall the transformation which takes you from the Bernoulli random variable to the 2-point random variable. Apply this rule of variance, because these two are independent. Yeah, the random variable, Bernoulli random variable, is independent of this deterministic quantity. The variance of a deterministic quantity is 0, yeah, plus this coefficient squared. Remember, you can either take it as a times 1, so it will be a squared times variance of 1, or you can say a, so it's simply variance of a. In both cases you get a 0. So you know how to work out the variance of the 2-point distribution. You have to be very careful. I have included a trick question here. Let's pick the same variables from the previous example. In the previous example, x was Bernoulli distributed with probability p of success, and y was a transformation, the 2-point distribution. It was simply it was a plus b minus a x, if I remember correctly. It was a plus b minus a times x. Yeah. So I have two random variables, and let's say I want to work out the variance of the sum. So if I'm a mindless student or a teacher, what will I do? I will simply say, okay, variance of x plus y is variance of x plus variance of y. So I just plug those two values and I get this. But this is wrong. This is basically wrong. Why? Because x and y are not independent. Y is a transformation of x, so how can x and y be independent? They are dependent. Y depends on x and x depends on y. It's either way. So a more careful approach is to start with this summation, plug the value of y. You will not have that much luxury every time, but now we have it. Simplify it, bring it into that form so that b minus a in the previous example is now replaced with b minus a plus 1. The rule doesn't change. This still goes to 0, and now you have your variance. So you need to know how to apply these different formulas. Another interesting scenario is when you have several Bernoulli trials. Let's say you have n Bernoulli trials, and the success indicator in each trial is a Bernoulli random variable. So xi in the ith trial is a Bernoulli random variable, and you know that each of these indicators has mean equal to p and variance equal to p times 1 minus p. We just discovered it in the above example. P times, you see, the success probability times the failure probability is the variance of a Bernoulli random variable with p as its parameter. So now we have n random variables all having the same variance. So what if I want to work out the variance of the sum? Now that sum will represent what? That sum will represent the number of successes, because you are adding ones and zeros, and zeros represent successes, zero represents a failure, 1 represents a success. So when you are adding ones, you are actually counting the number of successes. So these are independent, definitely, because when you say Bernoulli trials, Bernoulli trial by its very definition indicates independent as well as identical. Identical means that you have the same probability of p of success. So variance of the sum of these random variables, the Bernoulli random variables, the sum of variances, each variance is p times 1 minus p, so you just multiply it by n. So you see how easy it is to determine complicated variances by a simple application of these rules. So sometimes we need relationships between the variance and some useful expectations. So here we have an expectation of x squared. Yeah. So I just take square of x and I want to find the expectation of that. So how can I connect this to variance? So I can I still go with the square. I add and subtract the mean because I want to connect it to variance so that I can see that x minus mu. Apply the square, expand it, use linearity of the expectation and recognize that the expectation of this simple difference without squaring it will be 0. So you have a very nice formula. The expected value of a squared random variable is simply the variance of that random variable plus the square of its mean value. Yeah. So you can also remember it in words. Yeah. The expectation of a squared random variable is the variance of that random variable plus the square of its mean. Another useful quantity is the expectation of this transformation, x times x minus 1. So x times x minus 1 is interesting because in my lecture in which I introduced the telescoping sums, there you found out that summation of k times k minus 1 appears frequently, and it is very easy to deal with that by using the telescoping series. So you see this k times k minus 1 will be a possible value of x times x minus 1. So why not try this as my expectation of x times x minus 1. So expand this, x times x is x squared minus x, apply linearity, expected value of x squared minus mu x. So I can now plug that, basically ex squared is that, I just plug it here and I get a new relationship. I can even use arrange this by leaving this variance on one side and bringing this to the other side, and I have this nice relationship. You do this at home, but try to remember the pattern. The pattern is this: variance of x can be written in two ways. You either write it in the form of these falling factorials, yeah. So you can think of it as the falling factorial x 2 factors minus, this is also a falling factorial, the mean, and you just take the falling factorial. You can either remember it this way, or you can also remember it in the form of squares. So actually I'm using that now. So if you solve this equation for variance, it will be the expected value of the squared random variable minus the square of the expected value. I think this will be very helpful for us. It will be more convenient to either compute this, and for some problems, for other problems it will be convenient to compute this. So you can use either of these two. Computing variance directly will be difficult. It was easy in our case because we were using transformations. If you don't have transformations, then computing variance by the original definition is very difficult. So just remember these two formulas. Let me say it again. The variance of x is the expectation of the falling factorial, yeah, minus the following factorial of the expectation, or the expectation of square of it minus the square of the expectation. Yeah? So expectation of square minus square of expectation. Expectation of falling factorial of expectation. You see, there is some actually rhythm as well in remembering this. So let us try the variance of a uniform discrete distribution. Uniform distribution is written this way. Yeah, this n reminds you that I have values 1 to up to n, and they all have the same probability, 1 over n, and I want to know the variance of x. Now directly attacking this will be difficult, so I should try this falling factorial, yeah, x falling factorial. If you look at that, if you actually watch that lecture again, the telescoping method, I just apply the value Yeah, I just add these values, k times k minus 1, 1 over n is the probability, and the sum of such products can be used by the telescoping method, and I will get my answer. And now if I want to know the variance is simply, I can use this result. The variance will be the expected value of this falling factorial minus the falling factorial of the mean. Now I already worked this out, so I just plug it there. Yeah, n squared minus 1 over 3 minus, I already know the answer. I know the variance of the mean of the discrete uniform, standard discrete uniform distribution. That was, if you remember, mu x was n plus 1 over 2 times n plus 1 over 2 minus 1. Simplify this and you will get your variance. So on the next page I have worked it out for you neatly. You follow this and you get this nice expression, n squared minus 1 over 12. If you try this by using the formula of x directly, let me tell you, you will be in trouble, because that sum will just get out of control. And if you now want to move from the standard from the standard discrete, from the standard uniform discrete distribution to the distribution where you don't change the probabilities, but you just start from A to B. Yeah, instead of 1 you start from A, and instead of n you end up at B, and these are still integers. So you can simply use this transformation. You go from the standard x, actually if I remember it correctly, yeah, you simply add to this a minus 1. Yeah? So that when x is 1, 1 minus 1 will cancel out, you will get a, and when x is n, you will get a minus 1 plus n, which is b. So I just apply variance to this transformation. Now variance of y will be equal to variance of this deterministic quantity time plus variance of x. I know variance of a deterministic quantity is 0, so variance of y is variance of x, and actually it's the same quantity. You simply need to plug n is equal to b minus a plus 1 and you have your formula. In most of the books you will see this formula, but in some books you will see this formula, depending on whether they use this form of the distribution. Remember, how did we represent that? We write u discrete, d for discrete, and write n as a subscript. When you have one subscript, it means that you go from 1 to n. So this reminds you of the last value. When you have two values, this is different from 1. You use the same symbol d, ud, and instead of one subscript, you write two subscript. Whenever I use two subscripts, it will automatically remind me of this. When I use one subscript, it will remind me of that. This is the standard discrete uniform. This is the general discrete uniform, or the transformed one. I can also apply these nice results where I take two independent random variables. The variance of the sum is the sum of variance. I can also apply this to the two die straw experiment. Yeah. So if you remember, you had two dies, and the number of dots on each die can be represented by a random variable. So xy could represent the number of dots facing up one of the die, and you know that if the die is fair, it will be a uniform discrete distribution with 6 values from 1 to 6, and x2 for the second die will also be uniform discrete with 6 values. I also know the variance of x1. What is the variance of x1? Yeah, it was n squared minus 1 over 12. What is n squared? N is 6. So both of these random variables have the same variance, 6 squared minus 1 over 12. So I just add 6 squared minus 1 over L 2 times because they are the same, and I get my variance. So I think that was it for today. So next time we will start our new topic, and that is, yeah, just remember this name, PGF. You will know what we mean by PGF. So stay healthy and see you next time.